Why is software architecture so hard? Let's figure it out. Back in 2015, I got a tech lead role for the first time. By then, I had enough experience and knowledge as a software engineer, so I thought, why wouldn't I ready? Then came the first meeting with business stakeholders, where I had to explain my technical decisions. And suddenly, I felt completely lost. It wasn't about how do I write the code. It was where do I even start? Is this design gonna be sustainable in the long run? Is this technology which I'm proposing a valid choice for a workflow at all? Won't this integration destroy our customer business? I felt unsure. I thought I couldn't answer this question because I lacked some knowledge. Years later, I realized that the problem was expecting certainty where it simply doesn't exist. At the start of a real project, those questions never have perfect answers. You only learn to make the best possible decisions with the information you have. That's exactly what the book Software Architecture: The Hard Parts tries to resolve. It's essentially a framework for modernizing legacy monoliths into distributed architectures without destroying your company business along the way. I recently read it, and I'm gonna provide you a spoiler-free summary so you know if this book deserves a spot on your shelf. First of all, who is this book for? I'd say it's a must-read for any experienced engineering roles. Senior engineers, technical leads, software architects. Solution architects may find most of the concepts already familiar, but still, the book does a great job of structuring your knowledge and putting it into a clear, practical framework. The main philosophy this book delivers is that there is no one-size-fits-all solution. Every architecture decision comes with its trade-offs. You want scalability, you're going to lose simplicity. You need availability, you lose consistency. Instead of chasing perfections, authors encourage a mindset of finding the least worst solution, the one that fits your specific problem reasonably well. This helps avoid architecture bias, like rejecting some patterns or technologies simply because they're not your favorite. Instead, it encourages evaluating trade-offs in context, your domain, workflows, constraints like budget and team skills. Patterns are tools, not goals. The book reinforces this by walking through a detailed example of transformation from a monolith to distributed microservices. The next big idea this book reinforces is how collaborative decision-making leads to better outcomes. Good architecture decisions never happen in isolation. They happen when product managers, data solution architects, and engineers get in a room and argue about trade-offs, concerns, and align on decisions. The goal isn't to make everyone happy, but rather to find a solution with acceptable downsides and meaningful benefits based on everyone's concerns. Sounds obvious, innit? Though I've seen quite many cases when solution architects drafted a design in isolation without any real support from the dev team. That's not to say that all these designs were necessarily bad, but they were often like templating based on past experience rather than proper context-based decisions. So after reading this book, I just reaffirmed how architecture view is important, especially on the large mission-critical projects. To make architecture decisions explicit and durable, the book promotes architecture decision records, or simply ADRs. Each ADR answers 4 questions. What decisions are we making? What alternatives were considered? Which option did we choose and why? What are the consequences? This approach works because it forces clarity without heavy governance. In practice, simple ADRs often outlive complex documentation systems. The book also introduces architecture fitness functions, automated checks that protect architectural qualities like coupling, dependency rules, or performance thresholds. When integrated into CI pipelines, architecture becomes continuously validated and not just formally discussed. One of the central technical ideas of the book is coupling. 2 parts of the system are coupled if changing one may force changes in the other. Coupling directly limits how system can evolve. From this comes the concept of architecture quantum. an independently deployable unit with high internal cohesion and controlled external coupling. A microservice is a common example. The authors distinguish static coupling, which is compile-time dependencies like libraries and frameworks, and dynamic coupling, which is runtime communication between services. Dynamic coupling, especially synchronous calls, has a major impact on scalability and resilience and must be managed deliberately. All distributed workflows the book proposes to review through three core dimensions: communication, whether it's synchronous or asynchronous, consistency, atomic or eventual, and coordination, orchestration versus choreography. By combining these dimensions, the authors describe 8 saga patterns, each representing a different combination of coupling, complexity, availability, and scale. The key takeaway is simple: architecture decisions must be made per workflow and not once for the entire system. Some workflows, especially those around critical business data operations like payments, require synchronous communication and strong consistency. Others may benefit from asynchronous flow and eventual consistency to improve resilience and scalability. Another major theme of the book is architecting with data in mind. The authors clearly separate two types of data: operational and analytical. Operational data is what your business runs on: orders, transactions, inventory, payments. If this data is inconsistent or simply corrupted, the system fails. Analytical data is used for reporting trends, insights, and business intelligence. It's important for strategy, but not for day-to-day operation. Because of that, it can tolerate different consistency, latency, and storage models, and usually prioritizes availability over consistency. These two data types have very different requirements, and architecture decisions should reflect that. Then book dives into architectural decomposition. It explains how to break systems apart using component-based approaches and how to reason about dependencies using different types of coupling. To support decomposition, the book presents several concrete steps, such as identifying and sizing components, consolidating shared domain logic, flattening components, defining component dependencies, grouping components into domains, and eventually extracting domain services. Many of these patterns are reinforced with fitness functions to prevent architecture degradation over time. One particularly interesting technique is tactical forking. Instead of extracting services from a tightly coupled monolith, teams clone the entire code base and delete everything they don't need. This approach often works better in chaotic systems because deleting code is easier and safer than untangling deep dependencies. It's not perfect, but it allows teams to move forward quickly when formal decomposition is too expensive. The book then explores service granularity disintegrators to help identify when a service might be too large. For example, if a service is doing too many unrelated things, or when modifying one part of the service frequently impacts the other part, that might be a signal that the service is too coarse-grained. Scalability is another criteria. If different parts of the service need to scale at different rates, keeping them together can be inefficient and expensive. Fault tolerance is similar. When a failure in one area causes critical functionality in another area to go down, this is a good reason to think about service decomposition. Security requirements also matter. If some parts of the service require much stricter security controls than the others, that can justify splitting it. And finally, extensibility is a good indicator. If a service keeps growing to support more and more unrelated contexts, it's often time to rethink its boundaries. On the other side, the book also defines service granularity integrators, which signal when splitting a service may be a bad idea. For example, if you need strong ACID transactions across services, separation can add significant complexity. The same is true when services must communicate constantly as part of the tight workflow or choreography. Shared code and shared data relationships also act as integrators. If services rely heavily on common logic or on data that cannot be cleanly separated, forcing them apart can create more problems than benefits. The book then compares 3 reuse strategies: Code replication is all about clear boundaries, but harder change propagation. Shared libraries provide a compile time safety, but involves a considerable amount of dependency management complexities. Shared services reduce duplication, but introduce runtime coupling. Sidecars and service meshes help manage cost-cutting concerns, but introduce operational complexity. The next major topic is data decomposition. Key drivers include change control, when schema changes affect multiple services, connection limits, when databases become bottlenecks, scalability, when databases scale slower than services, and fault tolerance, when shared databases become a single point of failure. If multiple services share a database, they are effectively part of the same architecture quantum, even if deployed separately. The book balances with data integrators like strong transactional needs, tight relationships, or ACID guarantees that justify keeping data together. When decomposition is needed, the authors recommend a gradual approach, separating schemas first, then connections, then separate servers, and finally databases. The rule for data ownership is simple. The service that writes the data should normally own it. Problems arise with common or joint ownership when multiple services have to write to the same DB. The book presents techniques like table split, delegation, domain schemas, or service consolidation, each with clear consequences. When transactions span multiple services, classic ACID guarantees are no longer realistically achievable, which forces teams to rely on alternative consistency models. The authors review background synchronization, orchestrated request-based flows, event-driven eventual consistency. All of these approaches trade immediate consistency for better resilience and scalability. The book also reviews several approaches to storing analytical data. Data warehouses centralize analytical data, optimize it for reporting, and isolate analytics from production systems. This approach works best when business depends on a stable, trusted reports, things like financial dashboards, quarterly KPIs, or inventory metrics. Data is cleaned and transformed before it's stored, following a transform then load approach. The result is well-defined schema that makes reporting reliable and predictable. On the downside is rigidity. Changing schema or adding new data sources usually requires coordination and time. Data lakes takes the opposite approach. Instead of enforcing structure upfront, they follow a load then transform model. Raw data is stored first and transformed later, depending on the use case. This works well when flexibility and scale matter more than strict structure, especially in event-heavy systems like mobile apps or streaming platforms, where you collect clicks, logs, telemetry, or experimental data. Data lakes fit naturally with distributed and event-driven system, but they shift complexity to consumers. Without clear ownership and discipline, they can quickly turn into data swamps. Data mesh goes a step further by fully decentralizing data ownership. Instead of a central data team, each business domain, such as payments, logistics, or marketing, owns and publishes its data as a product. This model aligns well with microservices, asynchronous communication, and eventual consistency. However, it only works in quite mature organizations. Data mesh requires strong contracts, clear ownership, and solid platform support. Without those foundations, complexity doesn't disappear, it simply spreads across teams. That was my high-level overview of the Software Architecture: The Hard Parts book. I've only covered a small part of what this book really goes into, but what really stood out to me is how clearly it connects all the major concerns of distributed architecture into a single philosophy. Good architecture comes from grounded decisions, thoughtful trade-offs, close collaboration between key stakeholders, and making decisions explicit, along with the reasoning and documenting them. If you're a senior or lead backend engineer, or simply someone interested in modern, scalable architecture, I highly recommend reading this book in full. I hope this was helpful. If you liked the content, please hit the like button, and I'll see you in the next video.